All right, in this video, we're going to talk about a familiar topic from single variable calculus, substitution, but how we run substitutions with double and triple integrals, where we can actually do multiple substitutions in the same integral. Let's first talk about substitution for a single integral. And my first example, you wouldn't normally think of as using a substitution, but let's just work this out. The antiderivative here is just x to the fourth over 4, evaluated from 0 to 2, gives me 16 over 4, gives me an answer of 4. But if I wanted to, I'm just trying to make a point here. I'm not suggesting that you would do this one with u substitution. But if I did think of x cubed as x squared times x dx, and did a u substitution where I let u equal x squared, du would be 2x dx. And so x dx itself could get replaced with 1/2 du. I could think of this now as an integral. My x squared was u, and the x squared dx we see gets translated to 1/2 du. And if I convert my limits, remember, these are x limits. So if x is equal to 2 and I run it through here, that's going to correspond to u being 4. U would be 2 squared. And if x is 0, run it through there, u is going to be 0. And so what this is saying is the original integral, the integral from 0 to 2 of x cubed dx, which I can think of in terms of area. Here was my original integral, the area under the graph of y equals x cubed from 0 to 2, this integral. That's what that area is, which we know the area of that integral, the value of that integral is 4. This comes out to be 4. Equivalently, if I think about this in terms of area, I could think of this as the area under the graph of y equals u, like y equals x, just a diagonal line here, from u equals 0 to u equals 4. And if I could always remember that 1/2 could be brought out of the integral. So I could think of this as this is the area of this triangle right here, which is a triangle that is 4 by 4. The area of that triangle is 1/2 base times height. The area of this triangle is 8. This is 8. But if I took this area and multiplied it by 1/2, I would get the correct answer, right? This is 1/2 the integral of u du from 0 to 4. So there's this idea of what that's saying then is in some ways is that each unit of area here, if it gets, because that area totals up to 4, if I double it, right, each unit of area there, I get the correct answer. I'm sorry, if I take this area and half it, right, I get the equivalent area here, which is 4. Either way you want to think about it. This area here could be double to give me this area, or this 1/2 is saying if I take this area, which is 8, and multiply sort of each unit of area in this triangle by 1/2, it gives me the correct area of this integral where I did the substitution from. So we've never really thought about that, like when we do normal u substitution, like what does that number that you get to accommodate the du, how can you think of that in terms of area? It can be thought of as a shrinking or a compression factor. Here, the 1/2 I'm thinking of as a compression factor, that I take this area and half each unit of area to get me the correct area. Another analogy for what's happening when we do a substitution can be thought of in terms of, I like this analogy, thinking of a shadow on a wall. If you've ever got a light bulb here, right, and cast some light here, and if you had a smiley face image, and let's say you had a closer wall, it would give you a certain image, but if you move the wall back, you would get a larger image of the same thing. And so you can think of it as each point, this is all coming from the same image. So this smiley face here over here, each point in R must have expanded a little bit to give us this same image here when we move the wall back, so to speak, or for a different boundary G. Same image, but just smaller size. There's sort of a scaling factor that's involved there. Now, in this class that we have actually, unbeknownst to us, seen this expansion or contraction factor show up is actually polar coordinates. We know when we take a rectangular coordinate double integral and translate it to polar coordinates, we have this extra r dr d theta. In previous video, I sort of explained why the r had to be there, that extra r there. But another way to explain it is we can think of it as a expansion or a contraction factor, a scaling factor. This particular double integral in rectangular coordinates, y equals the square root of 1 minus x squared describes the top half of a circle. Y equals 0 is the x-axis. And if I go from x equals 0 to x equals 1, this double integral is simply describing this quarter circle with a radius of 1. This is y equals the square root of 1 minus x squared. This double integral is literally giving us this area, which we know is 1/4 the area of a whole entire circle. So this would be 1/4 times pi 1 squared, or just pi over 4. Okay, so that's actually the value of this integral. It's pi over 4. If we were to convert it to polar coordinates, we know the conversion. Theta would just have to vary from 0 to pi over 2. And r would go from 0 to 1. And while, if we think of with the true definition of r and theta and what they mean, that kind of, we recognize that as a quarter of a circle. If we just think of these as two variables, just two random variables, not knowing that r and theta actually represent angles and distances from the origin, another way to think of this is a rectangle. This could be thought of as a rectangle where theta goes from 0 to pi over 2, and r goes from 0 to 1. And if we think of it that way as a rectangle, then the area here is just 1 unit times pi over 2. It is pi over 2. And so, but we know the value of these integrals should be the same, right? So one way to think about this is that the area, this is what we're going to call G, our new image of our area. This was R, the original region. Since the area of G is larger than R, each point in R, kind of that same idea of the light bulb expanding the area, each point in R must have been expanded by the same amount. And in this case, that amount is this extra R right here is accounting for the change in the area from R to G of each point in there. So in this, I guess one way to think of it in this case is R, if R is now we think about as the distance to the origin, then the further R out, we're getting a bigger expansion of area. Anyhow, it all balances out. So it looks like, in fact, that this area is exactly double this area. So the question is, though, is how do we know for sure how much does each point expand by when we go from our original region of integration for the double integral to this new transformation into two different variables, and we get a new image that we're integrating over? How do we know how much each point expands by? Well, there's something called the Jacobian matrix. It's a determinant of a matrix, which we'll refer to as the Jacobian. The derivation of this is very complicated, comes from upper division math. So don't worry so much about it right now, unless you go further on. But what happens if you're doing a substitution with two variables, if you're letting x, normally in single variable calculus, we just let u equal one thing, right? And that's it. But now we have the ability where we can let x be something and y be something else, or u be something and v be something else. I guess that's probably more how it's going to look, right? Instead of just letting a U substitution, we can do a U and a V substitution. And the determinant of this matrix will give us the expansion or contraction factor. So the one we just did, for example, in polar coordinates, to show why that R has to be there. In polar coordinates, we really are doing two substitutions. We're letting X be R cosine theta and Y be R sine theta. So that would be, R would kind of be like my U, theta would be kind of like my V. These are just, any two variables here, right? So then my Jacobian matrix would be the partial of X with respect to R, partial of X with respect to theta, and then the partial of Y with respect to R and with respect to theta. So let's find those. The partial of X with respect to R, treating theta as a constant, is just going to be cosine of theta because that's a constant. The derivative of R is 1. The partial of R cosine theta with respect to theta, treating R as a constant, is going to be R, and then this will be negative sine theta, so negative R sine theta. Partial of Y with respect to R is just sine theta. And partial of Y with respect to theta is R cosine theta. Remember from 21C, the determinant is just the product of these two. So I'm going to get cosine theta times R cosine theta minus the product of the main diagonal, which is negative R sine theta times sine theta, which is going to give me R cosine squared theta. Two negatives make that plus R sine squared theta. And if you factor out an R, that's our favorite trig identity, cosine squared theta plus sine squared theta equals 1. So I get, there's the reason why when you do an integral in polar coordinates, why we have to have that extra R times the dr d theta. That's telling us our expansion and contraction factor. Similarly, in spherical coordinates, something we did recently, we know that our unit for dv, right, our unit for dv, when it's dy, if it's rectangular, it's just dz, dy, dx, no problem. But if you're doing spherical, remember it's rho squared sine phi or sine phi, d rho, d phi, d theta. So why is that there, right? Again, I sort of gave a geometrical picture that explains why that needs to be there, but we can also confirm this with the Jacobian. So if you have 3 substitutions, because we're replacing X with rho sine phi cosine theta, Y is rho sine phi sine theta, and Z is rho cosine phi, then I would need to do the partial of X. It would be a 3x3 determinant. Partial of X with respect to rho, partial of X with respect to phi, partial of X with respect to theta for all 3 of my variables. And this would take a little while. This is good practice to do, to actually take these partials. You'd have 9 of them to do. Partial of Z with respect to rho, partial of Z with respect to phi, partial of Z with respect to theta. If you work this out and do the 3x3 determinant, after a lot of work, this is not easy, you will get rho squared sine phi. I'm just going to say a lot of work using, I'm sure there's going to be some trig identities, so I'll put in parentheses with trig identities. Don't forget to use those to simplify it. And you will get this, and which shows why with spherical coordinates we have to have that rho squared sine phi. That's the term that describes the expansion or contraction, in this case, of volume for each little unit of volume. So you can try that if you want. Let's see how this actually can be useful now for just a regular double integral in rectangular coordinates. If I wanted to do this particular double integral, we can see that, nothing wrong with my bounds, but my first chore would be to integrate this stuff with respect to y. I'm pretty sure I could expand that out and integrate that with respect to y, but what am I going to do with root x plus y, right? I can't really distribute that even if I expand that out. it's going to be an issue to try to integrate this with respect to y or with respect to x. So if we were thinking u substitution, just the integrand here, integrand suggests, actually, I'm seeing two substitutions, because now we can do that. One of them, I would let u equal, normally your instincts with single integral substitutions, I would let u equal x plus y, and I can use a v for what's inside this one, v equals y minus 2x. Now, what we have to do, remember that the limits here describe a region which we're calling R. And we're now going to have our integral. Our integral is going to be the square root of u times v squared, right? With these substitutions. But we have to find out what our new image of this region R is in terms of u and v. And this is a long process. So how we're going to do this, let's first of all sketch, let's actually sketch what R is. Okay. Let's get this over here. The original region was described using vertical cross sections. So I can tell y equals 1 minus x is my top bound. That's a line with a y-intercept of 1, slope of -1. So something like that. Y equals 0 is my bottom bound. And this tells me from x equals 0 to x equals 1, which would be where y equals 1 minus x. So this is x equals 0. So this is my region R, this right triangle. What we now want to see is what does that region look like in the UV plane if I do these substitutions. So I need to solve these for x and y in terms of u and v if I'm going to do that. And there's many ways to do that. What if we solved this one for y equals u minus x, and if we solve this one for y is equal to v plus 2x, then that suggests, since both of these are equal to y, that u minus x equals v plus 2x. Which means, let's move the x over here, the v over here. So I have u minus v is equal to 3x. So x itself, I'm going to divide by 3, and I think I'm going to just go ahead and split it up. X is 1/3 u minus 1/3 v. That's kind of important. We need this. We also need to solve for y. And there's ways I could do that. So for example, if I were to put x right into one of these, maybe now that I'm looking at it, yeah, it doesn't matter. I've already drew the arrow to here. If I put this into here for x and isolate and solve for y, you can show that y, let you do the work here, y would be equal to 2/3 u plus 1/3 v. So make sure you can do that. Put that in there, simplify things. You should get this. And so now what we want to do is see what this image, we have some conversions for x and y, and we want to see what this region, which we know is bounded by these three equations, what it looks like in the UV plane. So, but now find new boundaries for G is going to be our image in the UV plane, in the UV plane. And so just to get organized here, we have 3 boundaries here. So we're going to, one by one, convert those boundaries into U and V. So let's make a little table here. So we have our XY boundary, and this would be for R. And we're going to convert this to a new UV boundary, which we'll refer to as G. So let's start with, how about just x equals 0? That's one of my boundaries in R here. Well, if x is equal to 0, that means 1/3 u minus 1/3 v equals 0. And if you solve it, usually u I'm going to treat like x, v I'm going to treat like y when I'm graphing in the uv plane. So I'm going to solve it for v. Well, that's just the same as 1/3 u equals 1/3 v, which is just the same as v equals u. That's kind of like y equals x. So this boundary, this left boundary in the xy plane is the equivalent to v equals u in the uv plane. Another boundary was y equals 0. Well, if y is 0, that means that 2/3 u plus 1/3 v equals 0. And if I solve that, I have 1/3 v equals negative 2/3 u multiplied by 3. That gives me v is equal to negative 2u. That's also another boundary for this one. And then finally, the other boundary, y equals 1 minus x, my hypotenuse here, this one's not going to be fun, but I have 2/3 u plus 1/3 v, that's my y, has to be equal to 1 minus x, 1 minus 1/3 u minus 1/3 v. Just putting these conversions in for each variable there. So let's simplify this. This will be 1 minus 1/3 u plus 1/3 v. You can see that the 1/3 v is going to cancel out. I'm just going to get, if I add 1/3 u to 2/3 u, note I just get a nice even u equals 1. And so if I put these together, we now have, in graph my new region, which we'll call G. Actually, let me use this region here because I can see I'm going to need a little more space here. One graph is v equals u. That's just a like what this is v, this is v, this is u. That's just a diagonal line like this. The other boundary is v equals negative 2u. That's going down with a steeper slope. V equals negative 2u. And u equals 1 is kind of like x equals 1. That's just a horizontal line. And this region here is our new region G. So remember the analogy, we're transforming this original region from our original integral, converts to this, but as we saw with the Jacobian, there could be some contraction or expansion of each point in R as it moves to G. We need to find out what the Jacobian is, because that's going to measure how much we need to expand or contract each point in R. So let's find the Jacobian next. Whoa. So now find the Jacobian. Remember the Jacobian, in this case, is going to be the partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. And let's put, it's not in view here. Remember, we already solved for x. X was equal to 1/3 u minus 1/3 v, and y was 2/3 u plus 1/3 v. Partial of x with respect to u, treating v as a constant, is just 1/3. Partial of x with respect to v is negative 1/3. Partial of y with respect to u, v's constant, is 2/3. And y with respect to v is 1/3. So my Jacobian is the product of this one, 1/3 times 1/3 minus the off diagonal negative 1/3 times 2/3. So that gives me 1/9 minus minus plus 2/9, 3/9, which is 1/3. That's my Jacobian. All right, so we're just about there. Remember, and I'll just go ahead and sketch it again. It's not in view here. When we converted to our new region G in the UV plane, we had this. So our integral is now going to be, and so you're kind of back to sort of rectangular coordinates. You have a choice whether you want to integrate with respect to v or with respect to u first, kind of like dy dx or dx dy. This would work out much better if we use vertical cross sections to describe g. So we're going to integrate dv first and then du. Let's put our bounds here for g. Every vertical cross section hits v equals u on the top, v equals -2u on the bottom, which is true as long as u is between 0 and 1. What are we integrating? Remember, we made these substitutions for these messy. Remember, we had root x plus y and y minus 2x squared. So this is really the square root of u, and this is really v squared. Square root of u, v squared. And the Jacobian is that sort of that expansion or contraction factor. That means we have to then multiply all of this by 1/3 to get the correct answer. That's our, I guess in this case, contraction. It means the region here is actually smaller than the original XY region. And this is a much more simpler integral to do. So I'm going to integrate with respect to v first. This will stay 0 to 1. U stays constant, so I'm going to have root u v cubed over 3. Let's go ahead and pull the 1/3 out because that is a constant. I can pull that out. Evaluated from v equals u to v equals -2u. And I'll integrate my result with respect to u. Let's go ahead and write this as u to the 1/2. When I put in u there, I get u cubed over 3 minus, if I put in -2u and cube it, it's going to be minus 8u cubed over 3. U cubed over 3, that's going to be plus 8u cubed over 3 is really going to be 9u cubed over 3. This becomes 9u cubed over 3, 9u cubed over 3, which is really just 3u cubed. If I pull the 3 out and multiply it with the 1/3, that's now going to just turn into 1. If I add the exponents, u to the 3rd times u to the 1/2 is u to the 7/2. Antiderivative of u to the 7/2 is u to the 9/2 over 9/2 or times 2/9. Evaluated from 1 to 0 is going to give me 2/9 times 1 to the 9/2, which is just 1, minus 0, 2/9. So my final answer is 2/9. As you can see, there's a lot of work that goes into evaluating a double integral with a double substitution. So these problems, just plan on they usually take a bit of time. And I'm going to stop this video and I will make another video with another couple examples so you can see, get more practice with this.